Okay, so now we'll prove theorem 414 in Rudin, which is if you have a continuous function from one metric space to another, then the image of a compact set is always compact. Or to say it in kind of a more catchy way, the continuous image of a compact set is compact. Okay, we've already seen that this works in R, but let's verify that it works in arbitrary metric spaces. And you really can copy and paste the proof from Abbott if compactness is defined to be sequential compactness, but we have never looked at how this works for topological compactness. We did prove that sequential and topological compactness are equivalent for Rk, for k-dimensional Euclidean space. In that context, it was easy for us, or relatively easy for us to prove because we had the Heine-Borel theorem. But we have not proven that sequential and topological compactness are equivalent in general metric spaces. So that result is not available to us. Therefore, we have to use topological compactness and make sure that this result that we had for R still works for general metric spaces. Okay, so let's assume the hypotheses, which just means assume that f is a continuous function from x to y, and assume k is compact. Then how can I prove fk is compact? I need to show that every open cover of fk has a finite subcover. So let's let G alpha, running over an arbitrary index set J, be an open cover of fk. And can we find a finite subcover? So somehow we have to use the fact that every open cover of k has a finite subcover. So how can I make use of that hypothesis, that every open cover of k has a finite subcover? Well, here's a convenient way to get an open cover of k. Take the preimages of the G alphas. So then if I take the preimages of the G alphas running over alpha and J, that should be an open cover of K. So let's verify that. There are two things to verify: that every set in this family is open, and that their union contains K as a subset. Okay, well, openness, for that we can use our previous result, that continuity of F implies that the preimage of an open set is always open. So these are all open. So we get to put the adjective open there because F is continuous. Okay, so when people say the continuous image of a compact set is compact, this is where continuous gets used. The preimage of the open sets in an open cover end up being open. Okay, and why do they cover? That's just some set theory. So if I take the union of the preimages, then that's the preimage of the union. And since the union of the G alphas contains as a subset Fk, I'd like to argue that the preimage of the union contains as a subset K. So let's just talk that through and verify that this inclusion works. Let's take an arbitrary point P in K. Then f of P is in the image of K, Fk. So f of P is in Fk. Therefore, f of P is in at least one of these G alphas. Then P is in the preimage of the union of the G alphas. I feel like my argument actually directly proved the inclusion K here. Maybe it is worth writing out. Okay, so temporary argument. Let P be in K. Then Fp is in Fk. So Fp is in Fk is a subset of this union, so Fp is in this union. And so P is in the preimage of the union. Okay, so we have ourselves an open cover of K, so there's a finite subcover. So let's move here. A finite subcover of K, so a finite subcollection of this family. So let's say indexed by alpha 1 up through alpha n. And to say that this is a subcover of K is to say that this contains K as a subset. All right, so what was our goal again? Was to prove that there's a finite subfamily of this family of G alphas that covers the image of K. So the claim now is that if I take only G alpha 1 through G alpha n, then that's enough to cover Fk. And if we prove this claim, then we are done. We're done because we've got a finite subcover of Fk. So to prove the claim, let Q be any point in Fk, and now my goal is to show you that f of Q is in at least one of these G sub alpha sub i's. So then Q is f of P for some P in K, but K is a subset of this union, so P is in at least one of these, right? Then P is in the preimage of G alpha I. For some I running from 1 through n. Therefore, f of P is in G alpha I. And I think that's it. We've now proven that this is a subset of the union. Okay, so the continuous image of a compact set is compact. That's a general fact about metric spaces. One thing I find interesting about this is that it's really pretty easy. I mean, this was all very straightforward coming from the definition of compactness. It's really pretty easy when you just use the definition of compactness. But if you try to prove this in maybe RK, where you have the Heine-Borel theorem, and instead of using the definition of compactness, you try to use closed and bounded. The continuous image of a closed and bounded set is closed and bounded. I find that to be really much less straightforward. In fact, I don't even know how I would start to prove that without going through the topological definition of compactness and using open covers. So I find that this really helps to, when you're only working in R or RK, sometimes you think, why can't I just use closed and bounded as my definition of compactness? This really helps to show you that the definition of compactness in terms of open covers is sort of the right one. It's the one that's more intimately tied to continuity.